Okay, good afternoon then. Well, as Axel's just explained, I'm Gent from Newcastle University, and in the second year of my PhD, working on supernova-driven turbulence, which means providing I can get this to work, if I turn it on, I know. Means I get to get lots of pretty pictures, hopefully. So, I'll try and explain exactly what it is that we're modelling. Here's a galactic disk, and what you see there is a box in the galactic plane, which in this particular case is 500 parsecs square and 2 kiloparsecs high. Most of the mass is in the central zone, and we have a gravitational field, and well, I'll explain what's in the model in a moment, but before I do, just go back to the start of the can, and the start of the video, and try and explain some of the features that's going on here. Those little spots that you see are simulations of supernova explosions. The density is highest in the middle there with the light colours, and as you go towards the edges, you get the dark colours indicating low density. We've tried to set it off with hydrostatic equilibrium so that it should actually retain its structure before the supernovas build up. But you can see that it did actually collapse a little bit before the supernovas start to build up. One of the features I would like to point out, so I'll just again take it back a little bit. Initially, it's all very well behaved. The supernovas are quite spherical, they're regular, they're controlled. But as you see later on in the simulation, you get some quite strange shapes occur, and then you get some explosions in the higher regions. And just now, see, that's a single supernova. And if you notice at the right-hand side here, it's actually bouncing off itself due to the periodic boundaries. So these are sort of things that we'll have to deal with to try and keep both the numerics under control and try and make it more realistic.
You're seeing density, right?
This is just density, yeah.
So is the disk completely broken up there or what?
Just about, yeah. It becomes very, very randomised. That simulation is without the magnetic field, the one you're watching there. And it runs successfully to about 50 million years before the time step goes to zero, because it becomes very difficult to resolve what's going on. So we need to correct that. Sorry, what's that?
What is being projected at the bottom there?
Oh, sorry, please get asked that question. That's a very useful one. So to explain what this slice is, the simulation we've been doing is a three-dimensional simulation. But what is being represented here is actually a series of 4 slices. The slice on the left-hand side here is basically a slice through the middle, showing the vertical direction. Then you have the other slice on the front is pretty much again through the middle in the vertical direction. The top slice is just slightly above the midplane, around about here, and the bottom slice at the very bottom is actually what's going on in the midplane. So they're just 2-dimensional slices. And although a lot of the illustrations I'll be giving are either 2-dimensional or 1-dimensional, they're all taken from data that is actually the full 3-dimensional simulation. Thanks for that question.
Right, and time is in what units?
In Geiger years.
Geiger years. So
this
37 million years is...
That's just that snapshot, but it did get up to just below 50 million. So, what are we using? We've got the shearing box to represent the fact that it's in a differentially rotating galaxy. And we're using, as Andor explained yesterday, basically there's not a typical galaxy, they're all very different. But we are, for the purposes of this simulation, using pretty much what we'd expect to find in our galaxy where we are. So it's set up with parameters which are very similar to the environment that we find our sun at the moment. The gravity profile is, to give an explanation of what's going on there, you've got the gravitational pull of the mass in the disk, and then you've also got the gravitational pull from the dark matter, and it gives you a gravitational profile that goes something like this. and goes to 0 and infinity. So, and it's only a Z profile, so gravity only depends on the Z direction, and there's no self-gravity. To get that isothermal hydrostatic equilibrium, we've just integrated that to work out what the density profile is, and again that's purely dependent on Z. This is just an initial condition, of course, and it's very unrealistic because the galaxy never looks like that, but we'll have to start from somewhere. And we have an isothermal, in this particular simulation, 8,000 Kelvin for the whole region to begin with. Obviously that changes once the simulation starts. And we also include radiator cooling, heating, and eventually, although not in that simulation, a regular magnetic field. How do we get the turbulence? Well, we introduce supernovas, and for that, I think we need to explain what we do, because it's very difficult to set up a supernova. So we have to sort of model one. In effect, what you have with a supernova is 10 to the 51 ergs of energy, which is the equivalent of about 10 to the 40 nuclear bombs, all being set up on the same spot. I'm not really sure how big that is, but I wouldn't like to be anywhere near it. And what that does is it basically heats up the environment around it to tens of millions of degrees Kelvin, creating huge pressures which result in massively supersonic explosions into the atmosphere. As you saw from that simulation, how that evolves will depend very much on the background, on the density, on the temperature, all sorts of profiles. So it's very difficult to understand exactly what's going to go on there. We can't really introduce a point like that in numerics. So to model our supernova, we start with a sphere, a regular sphere, and we add, in this case, we add the energy, which will heat up any gas that's inside that spherical area. And we, in our case, add 10 solar masses, although, to be honest, whilst it might sound a lot, 10 solar masses is completely negligible when it comes to the region of space that we're talking about. And these happen about 4 times per million years per kiloparsec. In this simulation that you saw, you get one supernova about just slightly more than once a million years in the size box we're looking at. What we can do, although we can't really clearly model what... Oh, and then what happens is this becomes very, very hot, and these shells start to expand. In fact, all the gas is expelled towards the edge, and very rapidly it starts to expand in the fashion you would expect. We need to test that, and I'll mention the Seeroff-Taylor model, which there I show the form of the equation from Dyson and Williams' interpretation of it. If you have an explosion into a monatomic gas with uniform density, it is actually possible to come up with this analytical model. And we've run these simulations and tested them against that model. Once the cooling starts to take effect, though, and the expansion is not purely adiabatic, the equation changes to the snowplow phase there. And it's possible to actually work out when that transition is going to take place using that equation on the bottom. So, prior to really getting stuck into the simulation, we tried running some of these tests to see what was happening. Now, I'm sorry that these look much better up on the screen, but they seem a bit difficult to work out from here, but I'll try and explain what's going on. Yeah, okay. So, the red plot here, that is actually the adiabatic solution analytically, given the conditions that we start off with. Run various simulations using different parameters, and the code behaves very well for the adiabatic solution. If you start off with a shell that is a radius of about 3 to 4 grid points, they all follow quite closely the red line. And what the blue line indicates is solutions which have kinetic energy as well as thermal energy. So what I mean by that is, as well as introducing, instead of introducing 10 to the 51 ergs, we introduce 5 times 10 to the 50 ergs in heat, and also introduce 5 to the 50 ergs in kinetic energy by introducing an initial velocity profile. If you start off with a small shell, they both behave very well, and they all follow this red line. We have 3 different simulations illustrated here that all should be in the same place. All I've done is I've separated them so you can see what's going on with the 3 different simulations. This is the one where everything is a nice small shell to begin with, and depending on whether you have kinetic energy or not, it doesn't matter a great deal. You get a good, it obeys the equation quite well. However, if you then increase this shell to try and keep the temperature down, which I'll come on to in a moment, then all of this is, the energy is then shared out in a much bigger region, and you find that you just don't get the acceleration, and that's what we're seeing with these green lines here, is that they're not following the plot. So we need to investigate why that was, and did some more work on it. This indicates the log plots, and you can see that irrespective of where they are, they do follow the analytic solution very well. They don't have the amplitude they should have for these green lines here. This here is just illustrating that, again, the code follows very well the Dyson similarity variable, which was given at the start. And this indicates how they behave at the snowplow phase. Unfortunately, the Zadov one hasn't printed out very well, but that goes up here. This is the this is the snowplow solution, and you can see that they're generally reasonably close to that solution, depending on whether it was a large initial shell or a small initial shell. That's the difference between these different plots, if you understand what I mean. So the radius here is half the size of the initial starting position of these. Now what was shown in this video, if I possibly pause it. No, that's something else. If you look at the profile of the supernova, these are line plots through the centre, through the origin. So here's the supernova shell, and we've taken a line basically going straight through the middle of the supernova and plotted what's going on with these various variables. In this case, we're looking at at the speed, the density, and the temperature. So the blue line is the density, and you can see that follows the profile that Anwar was showing earlier on that Murray Trophy had. So you've got basically a straight line outside the shell, very sharp spike, and then virtually nothing going on the inside. The temperature is illustrated in red, and the velocity is illustrated in green. So I'll just run that video again. Now what's interesting about this is we're running the simulations and finding that rather than having a peak of temperature just after you set the supernova off, when you would expect to have millions of degrees Kelvin, we were getting spikes happening long after the supernova. You can see sorry, is this the adiabatic version? Yeah, you can see there's a reverse shock coming in. I'll just again play that because I've missed it. Watch the green line on any of them, they all do the same thing. No, that's a small one. Sorry, let's start again. I'll get right one. Hang on, go back twice. My apologies.
Can you tell us which panel to watch?
Right, watch the one on the right here. You notice how on the left the velocity is going back up above the zero. So what you're getting is a reverse shock. So late on in the development of the supernova, you get the velocity field firing back in, it's very diffuse gas, and you get temperatures. Although these are all scaled down, so they all fit on the same plot, but we're getting temperatures of 10 to the 10 Kelvin. And how you're supposed to deal with that becomes very difficult. So we need to ensure that we prevented these high temperature spikes. And it was helpful to know what was causing them. But it doesn't matter which simulation you use, they all get that reaction. The difference is, sorry, I also didn't explain what the different plots are. So I'll do that now. So the one on the left, the two on the left, you're basically starting with 18.75 parsecs for the radius. And you double that for the two on the right, so there's 37.5 parsecs for the radius, initial radius when you set the supernova up. The reason we're doing this is to try and work out why it was that we weren't getting the proper growth with the when we made it larger. And you can see from the one on the right here, the temperature just drops phenomenally. So I'll play that again. So the one on the right, as soon as it goes off, the temperature drops, and you don't get the same sort of expansion going on over here as you do on the other three. The other three all perform equally well. The problem is we're trying to keep the temperatures down and still get the same sort of velocities and shock fronts occurring. However, some of these problems disappear when we move to the next one. This is the similar setup, but now we've got the cooling function. In this case, we're just using one simulation in the top left and both on the right are with kinetic energy. The one on the left is just the same plot that you saw before. What we're seeing though in the left-hand side, that's the cooling function.
Laser, not with your finger.
So, yeah, sorry, okay, thank you. On this one, you've got the cooling functions plotted, and blue is density still, all have the same density. This is what we saw before, temperature and velocity, and this is kinetic energy and thermal energy. Kinetic energy is in green, thermal energy is in red. I'll play that again. Now, we're now no longer, no, we're still getting reverse shock because that's the one before. We're now no longer, are you going to play? Play. Thank you. No, still getting it wrong. Right. We're now no longer getting this reverse shock. The temperature comes down and that helps to prevent this reverse happening so you don't get this spike as badly. But because of the cooling function, we now are getting very high temperatures developing. Now what's interesting here is that now the cooling function's gone to zero everywhere. Got thermal equilibrium everywhere here, but, sorry, the energies have gone to zero here. But this stays in static equilibrium, which when Amber was referring earlier, he says you get the cold phase and the medium warm phase sitting next to each other in equilibrium with equal pressure. Here we have the situation where you have the very hot phase and the warm phase, and that sits there in relative equilibrium. So the conclusion from that was that we need to watch what was going on with the cooling function because that was driving up these higher temperatures as well. We need to understand that. And also, we could use this kinetic energy quite safely without getting the reverse shock, providing we also had the cooling function. And the advantage of using the kinetic energy is that we can increase the radius of the supernova initial explosions. That keeps the temperatures down, but we still have the high velocities and the high shocks that we're looking for to get a realistic evolution of the core.
But if you really raise the temperature to 10 to the 10, the thing will not cool at all, right?
In reality, I mean, this is the cooling function. I'm pleased you're always spot on there. This is the cooling function here. This actually here is an unrealistic bit that is in the code because you don't get this sort of cooling. We've introduced that to try and stop getting these high temperatures. It's an artificial capping of the higher temperatures. But to explain what's going on, at different temperatures, you get a different effect with the cooling. In fact, I'm sure Amber went through that earlier on when he was going through Mari's talk. What is significant and was causing problems for our code, which we eventually identified, is that you have to have this very smooth. And I think, I'm not sure if you mentioned that earlier on about the code, no, but here what happens is if you've got a piece of space next to another, and it's at 100 Kelvin, or sorry, one's at 99 Kelvin, the other one's at 100 Kelvin, this one here is going to have massive drastic cooling, worth 252 in the code units. Don't worry about what they are, just look at the relative values of the units. That is multiplied by the density, which usually in a cold zone like that is going to be above 1. so it's going to be even bigger. So you're going to have this massive instability between the two phases, which cause perturbations. We, as we're running these simulations, even though we actually introduced a cut-off of 300 rather than 100 here, but we're finding that as you ran the simulation, the minimum temperatures were going down to just above 10 Kelvin. And we couldn't understand how this could be physically possible. Where's the cooling coming from if it's not coming from radiative cooling? Adiabatic cooling couldn't explain such large changes from 300 Kelvin down to 10. And it's because of the lack of continuity in this equation here was causing that. We also had another one here, which was rather an oversight on our part. These are based on the Rosen and Bregman cooling function. And they had, at this point, a value of up to 4 times 10 to the 7 Kelvin. We changed that to 10 to the 6, but didn't change the parameters. So what happens is you've got two values here, which differ by order of 10 to the 2 as well, in terms of the numbers that happen. So you have instabilities at this end, which would be increasing the temperatures at the high end. So this was reducing the temperatures too much. This was increasing the temperatures too much, and we're getting instabilities as a result. In the simulation that you'll be seeing in a moment, I've actually updated it to the version used by Mari and Axel in 2006, where they actually refined the continuity to like 20 decimal places to ensure that there was no possible instability. So the other problem we have with the code is dealing with the magnetic field, and why does that cause problems? This here shows what was happening to the mean speed of the gas. And as we have the magnetic field and the magnetic field increases, we've got this great spike, and basically the code just ran down to 0 again because it couldn't resolve these huge speeds that were going on. And what was causing it? It's difficult to understand. What would change is we'd introduce the magnetic field, so I'll explain what was going on with that. We initialize it with a field. The galaxy has a field of about 5 microgauss. So we introduced a 5 microgauss field, and it was just a horizontal field along here. And what we found was that we were getting huge temperatures, again, 10 to the 10 Kelvin, but you couldn't understand where that was coming from. And what it was the overheating as a result of perturbations going on up here where there's virtually no gas. So reduce the temperature, reduce the initial field just to a tenth of that, and we're still getting massive fluctuations in temperature and high currents. That is resulting. That's down to this term here, which is of the order J squared eta. Now eta we had at about 0.01, that order. J squared was 10 to the 3. So you're getting order of 10 to the 4 compared to the cooling function, which was about 10 to the 6, but then when you multiply that by the density squared, it comes way down. So this is actually overpowering the cooling function and creating further instability. So to deal with that, we had to introduce still a uniform field, but instead using the tan function so that basically most of the magnitude of the magnetic field is matched to the density, so you don't get huge oscillations away from the central zone. And that seemed to solve this problem. Well, it did solve this problem. Okay, so here we have the simulation. Actually, it's now 65 million years with the simulation. This again is the density. One of the other things that we did to try and prevent those huge shocks you saw in the first simulation was to restrict the height at which the supernova could go off. And I started to panic when I saw this beginning to be produced by the simulation, because I thought it's supposed to be like the other simulation, nice scale height of about 200, 500 parsecs, and it's all shrinking down the midplane. But eventually, supernova came to the rescue, and we see that it's starting to evolve a nice, chaotic, very varied and expanding frame. Again, the light colour there, that's high density, and the darker colours are low density. And you can see it's still evolving nicely, though it's got nowhere near breaking out into the halo. This then produced these results. We see that the mean speed saturates after about 20 million years. And that spike near the end there, that's just basically a supernova going off quite high. And as a result of that, or maybe it's near a pocket of supernova that already happened, so as it expands much faster. So you're getting quite random motions going on, but generally speaking, the mean speed is quite stable. And in this region here, between 10 and 20 million years, we get a growth, which looks exponential, and then looks like it saturates. This is the log plot of the same, and this gradient here is about 1, so it's exponential e to the t is the growth at that particular point. So, is this a dynamo? Remains to be seen. I'd like to run the simulation a lot longer and see how it evolves and make sure that we don't see this curve here perhaps continuing to go down. Perhaps we're looking to see if it goes up further. This is a plot of the max speeds. So this is the for the velocity field. You can see we get up to about 40, 50. Now, some of the earlier simulations I was trying to were falling apart. We were getting max speeds way over the 100 mark. And here, for the alpha speed, we're getting max speeds. I mean, that's up to 2,000, and the code is still dealing with it. But the maximum max speeds, we were getting like tens of thousands. And although the code could cope with it, eventually there comes a point at which it just can't resolve what's going on, and that's what we're trying to avoid. And we seem to have managed that. This is a video of the magnetic field in the x direction. So you see our initial field here, illustrated in red, is a uniform field in x, but very rapidly gets twisted and distorted. Again, my fear was that it was shrinking and was disappearing. But it comes back after a little bit of help from the supernova. Obviously, we're not just going to make pretty pictures. The idea is to try and understand what's going on here. But first off, we need to get the code to actually perform and produce something which looks like a realistic galaxy. At that early stage, it didn't look realistic. But now we're starting to see, as the code continues and it approaches, I think this finishes around about 60 million years, but it has continued beyond that. And you can see now it is starting to fill a much more realistic region, and we need to basically analyse what's going on here. This is, as I say, just in the x direction, and then the next one, this is basically the y field, which begins from nothing. Sorry, not y, this is in z. So this is the z component of the magnetic field, and it begins with absolutely nothing, and again will look very similar to the one we've just seen in terms of its shape and its magnitude.
The cooling doesn't bring material back yet?
Yes, it does.
Okay.
In this particular simulation, that's not happening at this stage. Well, at least not at the height that I've noticed it in the earlier simulation. But depending on what stage it's at, you do start to get cooling up here, and you can see, not with this so much, but with the velocity field, you can see that although generally in this region the velocity field is heading out of the box, there are phases where you start seeing velocity field coming back into the box as cooling occurs down here, and you see the mass moving back through the boundary, coming in from nowhere, regenerating down here. So that is where we're at so far. If anybody has any questions? All right.
Good. Thanks, Fred, for your interesting talk. And questions, please. What was the relative strength of the toroidal magnetic field versus the toroidal one versus boloidal? I mean, by which I mean BX versus BY.
Well, BY initially is 0. I haven't yet. These numbers have actually just finished running last night, so I haven't had a chance to go in and analyse in any detail the strength of the field. But that's the second simulation there, the video that you've seen, went from 0. And I would argue that whilst I couldn't put a number on it, the sort of magnitude of the field was beginning to catch up with.
So all the field was cross stream initially. So the
Yes,
first thing that must have happened,
purely in the radial direction.
right, was the action of the shear.
Sorry?
The first
shear.
thing that happened was action of the shear, which would amplify the magnetic field linearly.
Yes.
Yeah.
Very slightly though. The main effect was actually from the supernova explosions on smaller scales.
Okay. Okay.
Andrew?
Yes. Yes, please.
Did you say that on your second or third slide that you didn't have any cell gravity?
Yes. So we're just using the gravity of the region as a whole. So we're not trying to model what happens when you get very, very cold regions, because that's really on a level that is below the resolution we're interested in. So there's no need for that. Basically, the dominant gravitational force is the gravitation of the galactic disk itself.
But when the disk starts to spread out, would that not?
Okay, the gravitational field is based on observational information. We're assuming that the gravitational field, irrespective, our simulation initially is not a realistic condition. So what we've got is a gravitational field which is set up that hopefully if the simulation gets realistic, then we have a gravitational field which will remain constant and consistent with what we expect to see. Initially, you could say everything collapsing, and no, that wouldn't match the gravitational field. It would be quite unrealistic. But that's because in the real galaxy, you don't have this uniform gas which you start messing up. It's already messed up. But it's very difficult to introduce a messed up but realistic scenario. For instance, if you had it all messed up and then stuck a magnetic field on it, where do you put the magnetic field? If the magnetic field is supposed to match the gas and the density, how do you get it easily modelled to be fitting that? So we need the turbulence in the first place with a uniform magnetic field to create a fairly realistic but turbulent atmosphere. We can then go on and develop further simulations using that as an initial condition, but at least we know that the initial condition is a good one, we hope.
And what is destroyed is the gas disk. And what produces galaxy, the gravity field are stars. And all these events cannot move stars around, right? They are too weak for that. So the stars which produce gravity, they aren't mixed that violently. They sit where they want to sit.
I was also going to ask about something.
What was the numerical resolution of these runs? How many?
It's 600 high by 104 by 104. So it's around about 5 parsecs per group.
How many grid points for each supernova explosion?
That's a good question. We use about just short of 30 parsecs for the initial radius. So that's about 12, well, just short of 12 radius grid points, but of course that's in a spherical region. So it just makes it fairly stable starting conditions because you can resolve it quite well and it keeps the temperature down. But yeah. It still performs very well in comparison to an analytical test.
Yeah, I will just.
Okay. If there are no further questions, then let's thank Fred again.